after this week, which is supposed to be all snow days, next week we'll start doing like required work. You guys will have supposedly like an hour's worth of content per class period, and you'll have 3 things to complete and turn in each class. That's what we were told last. What that means to me is not very much, because I don't know if they're going to make us go in or not. I would prefer not to, because obviously I have all of this here and I'm like ready for you. So what I also did was I picked up one of these little guys right here. So if you've ever seen a Khan Academy video, the guy on Khan Academy uses this all the time. It's a tablet that lets me write, and I know you guys are excited because my handwriting's really good. It lets me write on the screen. So if I want to write on the screen, I can. I'm still new, so it's going to take me a minute. So there we go. I have written my signature note on the screen, but I've got it set up so that it can appear right over top of things. So my plan is to go ahead and load up some of these worksheets and stuff and just kind of show you. I do need to make the pencil mark a little bit thicker though, so y'all can see it. And then let's maybe pick a color that's pretty good. So let's test that really quick. Can you see this? See that okay? And the handwriting will get better as we go, once I get the hang. Oh, good. Yes, we can. That's really exciting. Cool. Awesome. So if you can see it okay, what's basically going to happen is worksheets are going to show up on the screen here, and then with my pen, I'm going to write. So hopefully, there's going to be some growing pains because I'm not super talented yet. So hopefully it works out okay. My handwriting is 10 out of 10. Yes, thank you. Very proud of it. All right. So let's get right to it here. What I'm going to do is show you guys a little bit about forces, and then we're going to do a little bit of work. Yeah, I got to do some mulching. Okay, yeah, that's fine. You can check this video out later on the YouTubes. I'm probably going to cut out this section, though, but it's been real. See you later. Don't forget to hit that subscribe button. Yeah. Okay. Let's get right to it. Today's going to be a little bit of an introduction to forces, and what I want you to understand about forces is that forces are a push or a pull, and they can cause motion. So there's a couple of different things that we're going to want to think about when we're looking at forces here. Let's pull up the forces cheat sheet really quick so you can see it. I'm going to zoom in on this guy for you so you can get a nice good view of it. Everybody's got one of these. I handed them out to you before we were all sent home, but I also have them posted right there on Google Classroom so you can check it out. So here's my forces cheat sheet. What you wouldn't understand is that forces have a magnitude, which is the size, and they have a direction, right? So both of those things are indicated by an arrow. So here we've got a box, and on that box there's a force that's 5 newtons, okay? That 5 Newton force is smaller than the force that's 10 newtons, and you can tell that it's smaller because the arrow is smaller, okay? So smaller arrow, smaller force. And then the arrow has a head at the end, which is indicating the direction that the force is in. So this is as though someone is behind the box pushing, and actually maybe there are 2 people, or one person's pulling and one person's pushing. This box here, the forces are the same size, 5 on each side, okay? So those arrows are the same size. That gets me to this idea of net force. So net force is the overall amount of force on an object. It's like the combination of forces. It's like math. You either add the forces together or you're subtracting them apart. So in this case, our net force on this box is 15 newtons to the right, because it's 5 plus 10 is 15, and it's all going to the right. But if you look at the second box down here, the net force is 0, and that's when you subtract 5 minus 5 is 0. So it's like there's no forces pushing on the box. So what we call it when the net force is 0, it's called the net force is 0. It's unbalanced. Sorry, I stumbled a little bit on myself. It is balanced. It's balanced forces. So 5 minus 5 is 0. The forces are balanced. This says something special about this object. The top one, the forces are unbalanced. So this object has a net force that's not 0. So if the F net is 0, the object is not changing speed. If that F net is not 0, the object will be accelerating. So in this case, the object's accelerating. So let's talk a little bit about what that means. Y'all probably know, and let me start a new sheet here. You probably know a little bit about Newton, right? So we're talking about, I'm going to have to find the pencil. We're getting there, everybody. Or you're probably like, you know, um, you're probably like, yeah, I know this. My sixth grade teacher made us memorize it, right? But what the heck does it mean? What it means is if there's something sitting still, or yeah, we'll call it sitting still for now. That thing is not going to move unless you move it, unless you push it, right? So, like, think about the chair on the ground in the classroom. It's going to stay there unless you push it. But if the forces acting on the chair are balanced, right, then the chair can move or stay still at constantly until it's changed. So think about the chair not moving. Its speed is 0. It's moving constantly with 0 newtons of force at 0 miles per hour, whatever you want to say. So it's not moving. And it won't move until you push it. That would be unbalancing the forces. As soon as you start pushing on it, you're applying a force in a direction, right? So it's almost as though we have, I'm going to try again because I'm desperate to get this to function. We have this box, and it hates me. There we go. We have this box, okay? And we're going to apply a force on the box. As soon as you do that, you're going to cause the box to move, and it will continue moving or speeding up until you stop applying the force, right? But if you, let's call the force a value here. We'll call it 5. Why does it do that to me? We'll call it 15 newtons or J5 newtons. Let me get my eraser. Just get rid of that. Oh, yeah, there we go. Oh, look, a subscriber. How's about that? Look, I even have little things for you to see dancing on the screen when you subscribe. Isn't that exciting? I have to recalibrate the old tablet here because it hates me. Okay, so 5 newtons of force. This object will continue speeding up with 5 newtons of force until you stop applying that force, or until you put another force going the other direction that is also 5 newtons. Ooh, nice. Okay, does that make sense? I'm sure it's probably not the easiest thing ever in the world, but the idea is if you have the forces balanced like this, then the object can stay either in constant motion or it's staying still. So this object here, let's say it was moving to the right already, going 10 miles per hour, and you balance the forces at it on it, it will continue moving at 10 miles per hour to the right. That's kind of how it's going to work. So that's what Newton's laws mean, and we're going to jump right back over here so we can take a look at them in a little bit more detail. Man, I practiced with the tablet, I swear. I was practicing with it all day yesterday, and I was getting pretty good. We actually want to open this. Oh, I gave you that's the wrong one. That's why. Here's the right one. There we go. Okay, so here's the first guy here. I'm going to zoom into that. This song has words. We can't have words in our songs. Sorry. There we go. Also, like, copyright. You know what? I'm going to pause the music because it's going on YouTube, and I don't want them to take it down for copyright purposes. All right. Sorry, everyone. Music's gone. Maybe I'll find something that's in the public domain for the next video. Okay, so the first one here, we've got a problem where we've got 5 newtons of force going up. Let's make that a little bigger because I think it's probably hard to see. Can I get it a little bit bigger? There we go. Just a little bit. Thank you very much. Okay. We've got 5 newtons going up. We've got a blank going down. And it says right here that our net force is 0. So the forces acting on the object are 0. Okay. Which means that whatever's going up has to be balanced out going down. So all we have to do is label this down one with a 5. If it lets us. Holy cannoli, everybody. I don't know why it keeps making that circle. It didn't do it all day yesterday. I was like a master at this, and then we start streaming, and now it's absolutely horrible. Don't worry, guys. We'll get it done. We'll get it done. Okay. I'm putting the number 5. It hates the number 5. Hates it. Let me write in free write mode, please. I'll pull up the settings really quick on this, homie. 10 seconds. Almost done. Disable all the clicks. Cool. That ought to do it, eh? All right, that should make this work. Okay, so all I need to do is make a 5. Why is it still doing the circle thing? It's like it hates me. Let's practice a little bit more, huh? There's a big old 5, big 5e5. Lots of 5s. Okay. I'm sure this is really amusing for those of you who are sitting at home doing your homework. Okay. And we're back. Okay, so you put 5 newtons on there. Almost visible. You get the picture, right? You put 5 newtons on there. I'm left-handed. I'm using my right hand. Oh, yeah, that's it. 5 newtons. Boom. Now those forces are balanced, right? So if we jump over to the next one, what I want you to see is that this next one is also showing you 0 newtons of force, okay? And it says, all right, there's 50 newtons going up, and there's 10 newtons going down. So what we want to do is we want to say, all right, we have to balance our vertical forces and our horizontal forces, because forces that are at a 90-degree angle to each other, they don't care about one another at all. They don't interact. So if they're perpendicular, they don't interact. So we need to balance our up and down and our right and left. Okay, so what I want to do to balance my up and down really quick is I want to make this, oh man, I want to make this 50, but it won't let me. Just let me make the same thing over and over again. Hopefully, if you're following along at home, you're like, all right, cool. So I know that you've got the top and the bottom balanced. Now what we need to do is balance the sides, right? So 10 on the left connects with 10 on the right. They cancel each other out. The net force is 0. Great. What about one where it's not that? Let's look at number 5. In number 5, the net force is 30 newtons up. Okay, so we know that this is relating to up and down. So what we need to do is balance our side-to-side forces. So there's 20 newtons going right. We need to put 20 newtons going left. I'm going to speed up a little bit because I'm concerned that I've lost a lot of my audience, all 4 of you. Boom, balanced, done. Now, we could balance the top and the bottom forces, right? If we put a 10 in right here. But it says here that the net force is 30 newtons up. So we actually need to make the top unbalanced. We need to make it 30 newtons bigger than the bottom. So what we're going to do is we're going to grab the pencil and we're going to write in 40 newtons. Is 30 newtons bigger than 10? Yes. So would we be going up with a 10 newton force? Yes, we would. So we will do that. Hello, dog. Wow. You guys want to say hi to my dogs? This is Chauncey, and over there is Neville. And yeah, they're loving life, just having a nap. All right, so I balanced my forces, okay? Except I know I have 30 more going up. That's how this worksheet works. Let's look at a different problem real quick. Oh, I just clicked on the wrong place. That was a big oopsie. There we go. Boom. Okay, so back at it over here. I know I've got 115 newtons going left. I'm supposed to have 15 newtons left. So what's 115 minus 15? It's 100. Okay, so grab your pen, and you're going to put 100 on the line. Sorry for that. It's a little messy. And then 10 newtons down, which means down needs to be 10 newtons bigger. That's 125 newtons. I told Mrs. Bauman not to text me. Oh, crap. I missed an important phone call. Jinkies. Object accelerate or not? And I'm here to help you understand. The object, if the forces are unbalanced, is going to accelerate. Okay, so this object right here, this one's going to accelerate. If the forces are balanced, then they're not going to. So this one does nothing. It can move at a constant motion. So either it's moving with 0 miles per hour, or it's staying. This is where having the pen that works would be really nice, because I could write this like 4 times faster to recalibrate the pen though, or it can stay constant. Okay, so you guys can have a good laugh at me trying to write with my right hand with a mouse. So that's like kind of one of the more important things to remember about forces. Now that's the easy one, in my opinion, is a document showing you about the direction and the magnitude of forces. What we get into next is also on the forces cheat sheet, so I want to show it to you. These are the types of forces we're going to be dealing with in my class. So in my class, we're going to be looking at things like gravity, okay, which we call Fg. It's like your weight. It is exactly your weight, actually. So the thing about gravity is that since it's weight, and weight is, we're going to write it down here in this open space. I have to select my, what is, man, mouse versus pen. Okay, so when we're down here, constant, okay, And what G is G is this thing. It's how fast objects on Earth are going to accelerate towards the ground. So 9.8 meters. Oh my gosh. Meters per second squared. And there's a video I want to show you about this. This says that all objects that are dropping, all objects that are falling through space, that are on Earth should be accelerating towards the ground, getting faster by 9.8 meters per second every second. So they should be speeding up by 9.8 meters per second every second that they're falling. And this is true for all objects in Earth's atmosphere. The only thing that changes that is if there's air resistance. So if you drop a ball and a feather at the same time, they should hit the ground at the same time, but they don't because the feather's held up by air resistance. And there's a video about that that I would like you to take a look at. I'm going to post it also after this on my channel, I guess. No, I'm going to post on Google Classroom because I don't own that video. They'll remove it if I put it on my channel. So you can check that out. But that's what gravity's all about there. So gravity is essentially going to always pull everything straight down. Somebody asked a question. I'm going to answer it really quick. The question is, do we have to go in today to get our stuff if we didn't go in on Friday? First of all, if you don't have your Chromebook, you really should go in and get your Chromebook if you need that. If you don't need your Chromebook, then you're probably fine. For my class, the stuff that's in there is the same stuff that I'm posting online. So you don't have to go in to get anything from me. If you wanted to go in, you may want to grab your textbook just because it's a good resource to have. I'm probably not going to assign anything in there, but if you are feeling insecure about it because you're like, man, I really wish I had that stuff, then go get it. It's in the school. If you go into my room, you'll see there's a note on my door that says, get this, get that, do this. So just check that out. But all these documents, yeah, they're all available for you on Google Classroom already. So you can just go to your Google Classroom page and you can see that. Oh, sorry, I just exposed somebody. Yeah, so if you don't want to go, then that's fine. And there are people there. The principals are required to be in this week, so they are actually there if you need to go get something. All right, so let's get back right into it here. Next force on our list is this thing called normal force. So that's what's going on in this diagram. As you can see here, I've got two boxes, okay? I've got a box that's sitting on the flat ground and a box sitting on a slope. Normal force is a force that's off of a surface. So if your box is on a surface, it's going to have this thing called normal force pushing straight up on it, or at a 90-degree angle to the surface. So straight up there, when it's on the ground, flat. If it's on a hill, the normal force is at a 90-degree angle to the surface. And that's, I did my best to make it 90 degrees, okay? The next force you could have is if something or somebody's pushing or pulling or throwing or moving or touching the box, there could be an applied force, FA, and the applied force is usually in the direction of the push or the pull, all right? Along with that, if somebody's pulling on something by a rope, then the force is usually called tension, which is FT. Anytime you see ropes, there's usually tension involved, so keep that in mind. And then finally, I've got my last two here. We've got this thing called friction. Friction is when the surfaces are rubbing together. On Earth, friction's like happening all the time, but in a lot of the problems that we're about to do, it says like ignore friction or don't account for friction or things like that. If it says that, you don't need to care about the frictional force. But in case you do have to care about it, usually the frictional force is going the opposite direction of the motion. In this case, you can see I made these little lines to show that the object is slowing down. Like it was going fast and now it's slowing down. Friction's causing that. So this is the unbalanced force going backwards. It's causing that to happen. There's still a normal force up and a gravity down, but we'll talk about that in a sec. Air resistance is basically friction in the air. So the direction the ball is moving, the opposite direction is basically the way the air resistance is moving. So if this ball is dropping, then air resistance is pushing straight up. If this girl is shooting this basketball and it's on its way up in this parabolic trajectory, like along a loop like this, then air resistance is pushing down and to the left against the path of the ball. Those are all the forces that we're going to be talking about in my class. I just want to kind of get started on one of these documents with you, and then I'm going to let you go because this is a really long video and I don't want to make it any longer. We're already going on 30 minutes, and that's not okay. Most of it's me screwing around with the pen, so I'm going to practice with that. Let's see here. How about the worksheet number 1? We'll do that. Let's start on this one here. I'm going to do like 2 here, and then I'm going to maybe do 1 or 2 on this document here, just so you can see them. These are all separate pieces of paper, but I post them all differently on Google Classroom. So if you're doing these, you can kind of get the hang of it with me as we go. So I want to explain why there's a dot. So the first thing here is this one says object lies motionless on a surface. This is a box sitting on the ground, right? Now, if we apply a force to this side of the box, come over here and use my drawing space. Oh, it's not showing up. That's bad. No, please show up. There we go. Okay. If we apply a force like over here, that's going to be different than if we apply a force over here or over here or over here. So to avoid that and making the box move in different directions and spin and stuff, we're going to take the whole box and we're going to smash it down into a single atom. Okay. So this is going to be our box now, and this is what we're going to draw on. It's called a free body diagram. Okay. This is where I really wish the pen was functional so I could draw arrows. It's going to be hard to draw them the right size without the pen, but we're going to try our best. Okay, so here it says the object is motionless on the surface. So what we need to know is this object it has balanced forces acting on it, okay, because motionless. So what we need to do is figure out what forces are there. For every single problem that we do like this, we're always going to start the same. Straight down. Oops, my apologies. I made it a little bit too long. Oh my gosh. I've never known a piece of technology to hate me more than this pen hates me right now. And we're going to call it FG for gravity. Okay, so gravity is going straight down. Just double checking the chat. What about the stuff in my locker, like folders, binders, other things? If you need to go in to get those things, go in and get those things. If you don't think you need those things, then don't. I mean, they'll probably just, if we don't have school again, they'll go through and they'll throw all that stuff away. So if you want something in there, or if you need it for other classes, you should go in. Most other teachers have you going in. Like if you have a language arts teacher who needs to read a book, it's probably sitting on your table and you need to go get it. So keep that in mind. Okay, so let's get back to the drawing here. So FG is going down, right? So that's a pretty big arrow, unfortunately. Sorry about that. I made it really big. But if we look at this problem here, that would not be balanced. This object would be accelerating through the ground, which it's not doing. So we need to balance it out with an equal and opposite force. Okay, so there's my equal opposite arrow. And what force is that? It's the force from the surface pushing straight up. So we're just going to label that F. In for normal force. Boom. Done. Right? So that's the first problem. That's how that's done. You're just labeling the forces there as they come. I want to do like one or two more on this page, so let's just randomly jump to one. Let's actually do number 3. I'm going to zoom into it because it's kind of hard to draw all these arrows on this tiny little space. Okay. Zooming in. Can I zoom in any more than that? No, it's not making it zoom in for me. That's really annoying. Don't worry, we'll get there, everyone. A lot of growing pains here the first couple of weeks because Mr. Bauman is decent at technology, but sometimes the technology doesn't like me. You know what I mean? There we go. That's working. That's the stuff. All right, number 3. The object slows down due to friction. Okay, so this is an object sliding on what's called a rough surface, a surface that has friction. If they say the surface is smooth, then you don't need friction. Okay, so I need to create my free body diagram for this guy here. So I'm going to get my pencil. What? Boop. And then I'm going to come over here and I'm going to create my circle. So we're going to make FG. Getting pretty good at it. And then we know that the object's not smashing into the ground. It's also not getting thrust up into the sky, right? So with a crappy line drawing tool, we're going to draw an equal opposite force, the normal force. These forces are balanced. Our object is chilling. Now, here we know the object's moving to the right, and you can see that it's slowing down. The question that we need to think about here is the object being pushed? It is not being pushed. It was being pushed, and then someone let go. It's like if you are standing in my classroom and you push a chair across the floor, eventually it's going to slide to a stop, right? While you're touching it, you're applying a force, but since nobody's touching this box, it's not being applied anymore. So there's no force pushing the object to the right. Okay, there's no force over here. But there is a force that's slowing this object down. It's going to cause it to stop, and that force is the force of friction. This is some people's favorite because it has 2 F's in it. I use a lowercase cursive s, or F, so that I can tell the difference between the capital F and the lowercase f. It's just like a thing that I do. You do not have to. If you want to use 2 capitals, it's your life. Okay, so that's that one. That's one of the harder problems at the beginning here, just because you're like, what the heck, isn't there a force pushing right? But there isn't. There's not one, so don't put it there. That would be an incorrect thing to do. Oh my gosh. Sorry about that. There we go. We're going to put our circle on here. It does not like fill colors. I'm sure you've picked that out. Okay. So we know we're going to have FG going down. Here The problem here is normal force on the box is not going at a straight up. It's going at a 90-degree angle to the surface, which means that normal force is going to be angled. Wow. That's not a straight line. I apologize. It's supposed to be, though. Pretend it is. Normal force is supposed to be going this way, right? Well, that's bad because now our up and down forces aren't balanced, which would cause the box to slide down the hill. But there's a little guy over here that's preventing that from happening, and that little guy is friction, y'all. Okay, that's how that problem works. It's a little bit more tricky, but I wanted you to see me do it so that you knew kind of what you were dealing with there. That's the end of that. Sometimes you forget and you do things. So sorry. Fixed. Second. Here's some more problems that are just like this. The top ones are pretty easy. You know, these aren't very hard, really. So maybe I'll just let you do them on your own. Let's deal with one that has, this girl is a gymnast. She's suspended from the bar that's hanging from the rope. I took out a lot of words here to save some space, and it sounds bad. Sorry about that. So I want you to see the problem done correctly, though. So there's a girl, and she's hanging off the rope here. And then I highlighted the whole page. Things are going so great. Okay, so let's look at her free body diagram. It's going to be really tough to squeeze this in, but we're going to try our very best. Okay, so we know she's got gravity. I'm making a circle. I should be making a line. We know she's got gravity. Pulling her down. FG. Okay. Now, this is different than the last couple problems because she's not on the ground, so there's no normal force. And here it says that a girl is suspended from a rope by a ceiling, or from a rope on the ceiling. So let's draw this picture so you can see it. All right. So it's like there's the bar, and it's tied to some ropes, and then here's our girl hanging onto it. Those are her arms and her head. And yeah, there's the rest of her body. Isn't that beautiful? Yeah, she's doing it, doing the gymnast thing. Oh, and this hand should probably be connected. Okay, so here's the thing. These ropes are holding her up. They're counterbalancing her gravitational force with something called tension. So you can either make two lines or one, but they should add up to be the same size as your gravity arrow because you want the arrows to add up to be the same sizes so that you can cancel out the forces. That's a big thing. That's FT, okay? And that's the whole story. That's everything I've got to tell you about. So that was a really long video. I'm really sorry about it. I know that it wasn't perfect, but we're going to try again tomorrow. So that's 40 minutes. I'm going to probably cut pieces of this out, but I'm going to stop recording it now.